So I think till last, that's mean today it is the eighth session. So in the previous session, we discussed about the periodic changes because of the periodic variations in the astronomical parameters, which leads to the various seasons we have. And in a long range, even the climate, it varies periodically. And we discussed that Milankovitch model, etc., not in details, but just give you the idea that how the insolation varies with the astronomical parameters, and that is the root cause of all climatic and weather changes. Today, we will now I will go to the hardcore positional astronomy. Now, positional astronomy, you already know that it is about the accurate understanding of the how the heavenly bodies uh, they move. The moving bodies are, of course, only the sun, moon, and the planets. So, and their study, their motion is very important because the motion of the sun, moon, they are linked with our seasons, etc. So, people always wanted to understand those motions here. Now, to understand those motions, they are very slow. So, one day observation will not lead to any kind of understanding of these motions. Therefore, it is essential to record the observed results for uh, ages actually. And to do that, what will be necessary. So therefore, what we have to do for quantitative record of the positions, etc., you all know that some kind of a coordinate system. So in case of the celestial objects, since it appears to be embedded in a celestial hemispherical dome or spherical dome, which is called the celestial sphere. So various types of celestial coordinate systems have been developed. So you'll have a very quick glance those, and you'll also understand that how, because with the understanding of these, it will be also possible for us to understand the positions where a particular day the sun rises or sun sets during a whole year. That calculation will be possible only when we go through a little bit of this quantification of positional data that requires a coordinate system. Now, for quantifying the description of the positions of the heavenly objects, it is essential to devise suitable coordinate systems. This is also essential for keeping records for future reference, because you have to keep the record for not only decades but ages or even generations. And therefore, this is only way to observe very slow or small variations of their positions with time. Astronomy is a subject that requires observation over very long periods and comparison of the data at regular long intervals. Therefore, recording the positional and other data is a very essential task for the astronomers. That requires to understand very well and robust system for positioning is important. There are different coordinate systems, and they are adopted based on the case of observation and convenience in utilization. In the ancient period, the coordinate system was most directly related to the observational framework. However, with the advance in the astronomical science, more sophisticated coordinate systems have emerged. Now, the major coordinate systems which are used are as follows. Horizontal coordinate system. This is the most obvious. That means we are standing on the surface of the earth and looking around, and we have a horizontal plane and horizon and sky above. And we fix a coordinate system with the observer at the central position. And that is considered as a horizontal coordinate system, which is the most obvious and directly linked coordinate system with the observer. Other coordinate systems are not directly linked with the observer, but they have a more scientific way of specifying the locations of heavenly objects. One of them is equatorial coordinate system, which is very similar to our terrestrial coordinate system like latitude and longitude. It is a very similar thing with different name. and they are also the two primary directions. One will be along the celestial equator, and other will be the meridian lines joining the North Pole and South Pole. Just in the case of Earth also, our longitude great circles are nothing but circles joining the North terrestrial pole and South terrestrial pole and the terrestrial equator. It is very similar. It is almost the projection of the same thing on this. But I think because of the precision of the equinox and few other slow changes over very long time, a more scientific method of specifying position can be done utilizing the ecliptic coordinate system is another one which is very important and we'll discuss. Finally, there is another coordinate system which we will not discuss because that will not be very relevant for as our ancient Indian astronomy is concerned, and that is called galactic coordinate system. Now, since these things are very recent and modern development, this fourth one will not be discussed. We will primarily take up the first three one. So you can see these are the, I said that horizontal coordinate system. You see, this is the horizontal coordinate system. This is the North Pole, this is the South Pole, and the observer is standing on the surface of the Earth here. So the plane, which is tangential to the Earth's surface, observer is here. Vertically above direction is called zenith, and this is the North Celestial Pole. But actually, along the horizon, you can always say that this is a north point. It is in the same line as the celestial North Pole. So this is called the north. Now, how you specify the position of a star? Now, you consider a plane containing this star and the zenith and O. This is the plane, almost quarter of a circular plane. Now, this plane, you rotate from when it is inside this. If you take how much you have to rotate to bring it from here to here, that means from the north celestial pole's north point and the observer, this is the reference plane. How much you have to rotate this, match this, that means this angle, the symbol capital A, is called the azimuth. And that is so far as it will give the plane in which the object is lying. Now, how high above the horizon? That is another quantity of the specified, and that is the altitude. That means this angle, that means this is the horizontal plane, and this angle is altitude. So capital A and small a, these are the two quantities which will specify completely the position of the celestial object. Now this is the horizon circle. It will be a circle. Obviously, you know that it appears to be circle like this. So this is the zenith. Bottom below is the nadir. This is the north point, the north celestial pole, and this is, and the quantifying thing is this, and the other one is there that I'll come to that later. That is called hour angle, which I'll discuss. So this is the most obvious and directly connected with the observer. So therefore, it is one thing is clear that it is dependent on the observer position. These two coordinate system, equatorial system, you can see this is the celestial equator and this is the ecliptic. Now there is a celestial object here. You want to specify its location. So you have to have a reference plane with respect to which you will consider the inclination of this plane. So it has to be a north celestial pole, and this is the equator. There is another line, you know, that is the ecliptic. You know that. Another great circle. And this point where they intersect, this is called one of the equinoctial point. The reference equinoctial point is always the parallel equinox. Now this, if you consider this position, this plane, and an object is say here. So you consider another quarter, this one. So this plane is the reference plane which passes through the vernal equinox, and this is the plane which contains the object. This angle, in terrestrial case, we call it longitude. Here it is called generally right ascension. Same thing, angle, but it is given in hours. So this will start at 0 hour to finally 24 hours to make a full rotation, not in degrees. So right ascension, it is a historical reason why astronomers use that. So this right ascension is actually given in hours, minutes, and seconds. If that means in time. So that will be the one which is equivalent to longitude. The other one, if this is the center, other one will be this angle, which is called declination. In place of latitude, it is called declination. And declination, if it is towards the north, then it will be positive. And if it is towards the south, it will be negative. In case of Earth, it is latitude north, latitude south, and here it is declination positive, declination negative from this. So here this declination and right ascension, these are the two quantities which are used, and it is very similar to the terrestrial coordinate system. Now the reference point is generally the vernal equinox. Very, very interesting thing which will come later. I will discuss that later. The other one is this one. This system is called ecliptic system. As I mentioned, similarly, you will find that here to consider ecliptic system, it will be again celestial sphere. This is the celestial equator, and this is the ecliptic. This is the center. So these are all great circles. So this is the ecliptic, which is very important because that is the line along which the sun and most of the planets are more or less along this. This is the north celestial pole, and this is also, there is another pole if you drop perpendicular to the ecliptic plane, that is called ecliptic. And how much will be this angle? You should know that. It is the obliquity. It is 23.5 approximately now, current value. Now the coordinate system is like this. That this is again the vernal equinox we use as a reference. So this is a great circle. What happens? This is the normal thing which I did here. In this case, what we do, we develop it separate from here to here. So this is the reference plane for ecliptic system. And if the object is somewhere here, then it will be, so this angle will be the longitude, and this angle will be latitude. Latitude is given by beta. That is the standard symbol. So you can see it is, here you did it with the help of equator and these meridian lines joining north celestial pole, south celestial pole. Here you take the ecliptic circle and the ecliptic poles along we get these great circles here. So it is similar system, only here the basis is this is defined as the longitude, lambda, and this is the latitude, which is again positive, negative, depending on whether it is towards north or south. So they are very similar. And but why this is important? Because actually that this point is slowly shifting towards west at the rate of 1 degree every 72 years or 52 Earth second per year. So therefore, what happened that following this, the longitude of a particular place, you can always say that with a reference here, and then how much you have to add if this has shifted towards west. So I will just mention here that in Western astronomy, this is always taken from the vernal equinox, which is definitely not constant because the vernal equinoctial point is shifting along the ecliptic. In Indian system, our astronomers started the reference point not this vernal equinox, but a fixed point on the ecliptic, which was the first star or the lead star of the sign Aries, মেষ রাশি। মেষ রাশির শুরুটা যেখানে হতো এইখান থেকে মাপা ইন্ডিয়ান সিস্টেমে হতো, এই জন্য বলা হতো মেষাদি। Point is called মেষাদি. So therefore you can see a basic difference. Indian system, the longitude is measured from a fixed point. It does not change with time. In Western system, the longitude is measured from a point which is slowly changing. So the value of longitude changes with time. And therefore, the Indian system is called Nirayana. That means with iron, it does not change. Nirayana system is the Indian system, and the Western system is called Sam. So you will see that I will again come to that and Nirayana. So Indian longitudes are Nirayana longitude, and Western longitudes are Sayana longitude. As I mentioned just now, so what are the coordinates in different celestial coordinate system? In horizontal coordinate system, it is the azimuth and altitude. Equatorial coordinate system, it is the right ascension and declination. And ecliptic coordinates, it is the longitude and latitude. These are the typical signs used. And our angle is one thing which I will discuss later. I have not discussed that now. We will come to that later. So now, a little bit of discussion, which these are just mentioned. Now let us see a slight more detailed discussion about this coordinates. Horizontal coordinate system, let us take first. So as I mentioned, that here is the observer. So this is the plane, tangential plane to the Earth's surface is the observer's horizontal. And this is the observer's zenith. And this is the observer's nadir. And this is the direction in which he considered it is north direction. So this is the north point. So when you do it in this way, you will find that this is the zenith, this is the observer, this is the north point. North pole will be somewhere here, depending on the latitude of the observer. So how we measure this? Sorry, this is the north direction. I am looking from the other side. So how much you rotate this plane containing the star and the observer, this plane, you have to rotate how much? You have to rotate by this much. That is called the azimuth, as I said. And this angle is called the altitude. How much is the height, angular height from the horizon? So this is what I have discussed. So azimuth and altitude. Now this system is dependent on the observer's location. This is something which the other two coordinate system, they have nothing to do with the observer, as you can see. It has absolutely no connection with any kind of observer position. But this one is directly connected to the observer and it's his position. So actually, but it is the most convenient. Suppose if Dr. Subrata Mandal wants to have some observation. Now he is located on the rooftop of your UEM, and that is the central point of his coordinate system. And suppose somebody in Kodaikanal is making some observation, so his horizontal plane will be different. So they are dependent on the observer. It changes position to position. So generally, for record keeping, It is always good. That means suppose you make some observation going to the top of the building and to the observatory, you get some coordinates. But for record purpose, that is not that suitable because everybody wants to use that data. So you have to convert that into some kind of a coordinate system which is independent of the other. So that we will discuss here. So first of all, the direct observation can be done like this and can be used, or you can use a coordinate system like this, which is called the horizontal coordinate. And what are the two quantities? Azimuth and altitude. So this is the same thing, but the language is different. So observer is here. This is the zenith. This is the east direction. This is the west. This is the north point and the north celestial pole. And the trajectory of all the objects, say for example, sun, will be like this depending on the day of the year. So azimuth will be from north to this, that means the whole angle. You have to always measure the angle from the north direction by definition. So this is the zenith. This is the north celestial point. The green is the horizon or horizon circle of the observer. Observer is standing here. And this is the north point. So you can have, suppose now there is an object, say here. So the earth is rotating like this, you can see. All planes are rotating about this axis. This is the earth's rotation axis. So I think you will find the, first of all, its location you can define, as you have said, by azimuth and elevation or altitude. There is another angle which is sometimes used. Elevation or altitude is from the horizon or horizontal direction. From vertical zenith also you can measure the angle, which is called the zenith angle or Z. And this is the elevation or altitude, which is called small lowercase a. Now another quantity, as I mentioned, which is important so far as, here again you can see. So therefore, as I mentioned, that this is the north celestial pole, this is the zenith, and this is the north point. So this is the reference plane, you can say. Now, when an object is there, you have to find out how much you have to rotate it. That is the azimuth. And how much is the altitude? That is this. That is not shown. This diagram is for another quantity. This is the what I have been showing, that if this is the celestial pole, this is the star and this object, and this is actually the equatorial system I have shown here. The reason is that, there is another quantity, because it is a local thing. Time is local time on which you are observing. There is another quantity which is used in this. It is called hour angle. This hour angle in astronomy is the angle between an observer's meridian. That is, observer's meridian is this one. A great circle passing over his head and through the celestial pole. And the hour circle is any great circle passing through the poles where some celestial body lies. Now, how much is this angle? How much is this? How much it has rotated? Now, you know that this is the axis about which Earth is rotating like this. So Earth is rotating in this direction, so things are appearing to rotate in the opposite direction. How much is it rotated from this position? This is the position which is given by your the planes, and the perpendicular to that, this one, which is perpendicular to the axis. That means this is the, frankly speaking, your equator, celestial equator. So how much this plane has rotated from the reference position here, that tells you that what is the time of the day when this observation is being made. That's why it is linked to the local time. So hour angle, because this is the one complication with the horizontal system, that it needs to be linked with the local time and the standard Greenwich time, etc. So therefore, this hour angle is something which also is important in this case. But so far as the position is concerned, the azimuth and altitude are good enough. But when you want to link with others, then this hour angle comes into picture. And this angle is expressed in degree. So this is the horizontal system, and horizontal coordinate system is fixed to a location on the earth, as I mentioned, and not the stars. Therefore, the altitude and azimuth of an object in the sky changes with time as the object appears to drift across the sky with the Earth's rotation. In addition, since the horizontal system is defined by the observer's location horizon, the same object viewed from different locations on Earth at the same time have different values of altitude and azimuth, obvious. So different observers will find that the same object at the same instant of time have different altitudes and different azimuth. This is though very convenient for observation purpose, but for record keeping and for finding the relationship with others, it is not that suitable. Anyhow, now the azimuth values for the cardinal directions are given here. The cardinal north point, obviously, north direction will have azimuth 0 by definition. East direction will have azimuth 90 degrees. South direction will have an azimuth angle 180 degrees. West will have 200 degrees. So therefore it is necessary that all these horizontal coordinate system data for record keeping is always essential to convert it to other coordinates. That is very important. Otherwise, it has no meaning because it changes from location to location, time to time, all these things. It is not a very universal system. Next, the equatorial system. As I mentioned, that equatorial system, I just drew that it is a natural extension of the latitude-longitude system used to locate a place on the Earth. The position of a place on the Earth is decided by two quantities, the latitude and the longitude. And figure shows that what are the things. Longitude is measured along the equator, and latitude is measured along a great circle connecting north and south. Figure the latitude of a place or a point is equal to the angle of an imaginary line from the center of the Earth to the point under consideration. With the equator, the longitude is given by the angle made by the meridian plane passing through the point with respect to a reference plane defined by a reference meridian line passing through Greenwich. Now, this is the modern system that the meridian plane or the plane connecting the North Pole, South Pole, and of course the center of the Earth, so which passes through a place in England, which is Greenwich. That is considered to be the reference and the longitude is 0. So you can see in the definition of longitude, there is certain degree of ad hocism. Why? Because long back, 1,000 years back or 1,500 years back, in Indian astronomy, the reference meridian used to be passing through Ujjain. So therefore it changes. There are some other times, some other place they used to have the standard the reference line from different place. But in modern astronomy, it is accepted as the Greenwich longitude is the 0 line longitude. So therefore, this is, say, for example, there you will see and the position of a place on the Earth just is done with X and Y coordinates on a flat plane, as all longitude circles, also called the meridians, are similar. One and the special meridian is chosen as the reference, which I just mentioned, and we call it 0 degree. And at present, the prime meridian passes through a place called Greenwich in England. In the ancient India astronomy, during the 3rd century AD onwards, the prime meridian is to pass through a city called Ujjain in India. As one goes towards east, the longitude increases up to 180 degrees. And if one goes towards the west, the longitude also increases up to 180 degrees west. So currently, longitude of a place is specified as so many degrees west or so many degrees east. Now, I think the latitude is important now, another coordinate. So although the longitude value has certain degree of adhocism, because you have chosen one particular meridian line to be of zero longitude, which is your choice. But latitude is not like that. Latitude of a place has very important natural relevance. The climate of a place depends upon latitude of a particular place, and it does not. It is not some adhocism, as you have seen. We have seen latitude circles are also they are not great circles, of course. Now, some very simple experiments with the gnomon can yield the true north direction and latitude of a place. I think this I mentioned that our students should do some hands-on simple experiment. Now, before that, they should practice a little bit of astronomy based on the sun. It's very simple. You need a day full of sunlight, not a cloudy day, so that something can cast a shadow. Now, before taking up the observational experiment, a little more about the sun's position in the sky, because it is going to be based on the shadow length, etc., of a gnomon, a shonku. So I think let us understand a little bit more about sun's position in the sky. Now, as I mentioned, latitude circles are different. Central latitude circle, that is the equator, is the largest diameter and divides the globe into two equal halves. The north hemisphere and the southern hemisphere, the latitude of a place, the northern hemisphere, up to 90 degrees, and that is the southern hemisphere, it is towards the south pole, minus 90 degrees. The latitude is the angular line joining the place with the Earth's center, which I have shown by my hand drawing, makes with the equatorial plane. The latitude of a place actually controls the temperature, and this I discussed in great details how latitude decides the insolation or the intensity of solar radiation falling on that particular place, and obviously, therefore, the temperature or the climate. When the sun during its yearly apparent motion along the ecliptic around these 2 points, the days are equinoxes, that is vernal equinox and the autumn equinox. So when the sun reaches the extreme positions, that is when its distance from the celestial equator maximum. So if I go to this one, say for example, so this is the system that is considered. So sun is here, and this is the equator. Now you can see that sun is always on this ecliptic. So you can see if sun is here today, its distance or the angular distance from the equator will be this much. That means this is the declination. If it is here, its declination will be more. On the summer solstice day, the declination is maximum. On the equinoctial days, the declination is zero. And in the winter time, as you can see, the sun will be here in the northern hemisphere winter, so declination will be negative. So declination varies from zero to a maximum, and again to zero, the other equinoctial position, then again a maximum in the other direction on the winter solstice day, again it will decrease and come to zero. So declination of sun, we have to understand before we can do any kind of experiment using the sun. And that's why I showed this. As I mentioned, the sun reaches the extreme position, that is the solstitial position. Its angular distance from the celestial equator is maximum. That is the declination will be maximum in magnitude. That you can see that this is the vernal equinox point. This is the celestial equator. So here the graduation is in hours, time. So 1 hour when you come back, which is equivalent to 24 hours. That is one complete rotation of Earth. And this angle, inclination, this is the right ascension, and this is the declination. The sun's declination here on the equinoctial days will be zero. It becomes more. It is maximum the summer solstice day, and then again it decreases, becomes zero, and go to the other directions. Now this information is important, and that is what is. It does not change with time. As you can see, there is change in the inclination of the ecliptic plane with the and the equatorial plane, this angle is nothing but the obliquity of the Earth's axis, which is, it varies little bit, which I mentioned, but approximately remains very near 23.5. This is what I mentioned. This is again the same thing, but here this is a star, not the sun. Here I'm showing the ecliptic in a better way. This is the ecliptic. This is one equinoctial point. This is the other equinox. So let me ask you, this equinoctial point obviously is vernal equinoctial. Why? Because here it is the winter solstice day, and after the equinox is the vernal equinox, spring equinox. This is the summer solstice position. So this equinox will be autumn equinox. Sorry, this equinox. This will be autumn equinox. So therefore, we plot it. It will be like this. So this is a very standard diagram used by all astronomers. This is the celestial equator, and you start from vernal equinox. The sun goes to the maximum position here in June with highest declination. Then again it becomes 0, and then again becomes negative maxima and 0. So this table is very important, and these are the, you can see, this is the, এটা সিংহ রাশি, এটা কর্কট রাশি, মিথুন রাশি, এইভাবে সমস্ত, এটা হচ্ছে মেষ রাশি এটা। So actually that's why when the sun is in near about Cancer and Mithun, that's the hot time. এটা হচ্ছে গিয়ে স্করপিও, বৃশ্চিক রাশি, এটা Capricorn. When sun is in this between Scorpio and Capricorn, then it is winter. Actually, that is why in ancient time people used to think that the heavens are controlling the affairs of the earth. Think like godlike situation, which of course now we can understand. It's a perfectly scientific explanation. So therefore, this I wanted to show you, sorry, that রাশিগুলো দেখে নিতে হবে। রাশিগুলো হচ্ছে এইগুলো, এই 12টা রাশি, এই 12টা রাশি এইভাবে গেছে। This is the ecliptic, and you know the রাশিগুলোকে নেওয়া হয়েছে along the ecliptic circle. এখানে এটা দেখতে এরকম ওয়েভি লাগছে, কিন্তু অ্যাকচুয়ালি ইটস এ সার্কেল। সেই আমাদের সিংহ রাশি, এগুলো সমস্ত, মিথুন রাশি, টাওরাস, টাওরাসটা হচ্ছে গিয়ে বৃষ রাশি, এটা মেষ রাশি, এইভাবে চলছে। এই টেবিলটা খুব ইম্পর্টেন্ট, and you will need to use this for your sun ray experiment. এখানে কি দেওয়া আছে? mean value for the 4 years of a leap year cycle. The leap year cycle আছে কিছু। তো কেন বছরের যে আমাদের ডেট গুলো, নাম্বার অফ ডেজ তো আলাদা, সেই জন্য লিপ ইয়ারটা তো রাখা হয়েছে। এটা হচ্ছে কি ডে 1। ডে 1টা হচ্ছে কি 1st জানুয়ারি। জানুয়ারির প্রথম দিনটা হচ্ছে কি এইটা, সেদিন সানের ডেক্লিনেশন হচ্ছে কি এত। ফেব্রুয়ারি পয়লাটা হচ্ছে এত, মার্চে এত, এটা কিন্তু নেগেটিভ, সাউথের দিকে, সাউথ এত, সাউথ এত, সাউথ এত। এপ্রিলের 1st তারিখে কিন্তু নর্থ হয়ে গেল, অলরেডি ইট হ্যাজ ক্রস দি 0.4 ডিগ্রি 18 মিনিটস। মেতে 14 ডিগ্রি 54 মিনিটস। 1st জুনে 21 ডিগ্রি 51 মিনিটস। জুলাইয়ের 1st হচ্ছে গিয়ে 23.9 ডিগ্রি, তার মানে অলমোস্ট পিক, দ্যাট ইজ দি পিক সামার। অগাস্টে হচ্ছে গিয়ে 18 ডিগ্রি, সেপ্টেম্বর আবার কমতে শুরু হলো। তো দেয়ারফর যে কোনো বছরের যে কোনো মাসের যে কোনো দিন, ধরি আমি বলি যে মার্চ 17th, কত? মার্চ 17th, এটা হচ্ছে 17th ডে, এটা হচ্ছে গিয়ে মার্চের 17th ডেতে ডেক্লিনেশন হচ্ছে গিয়ে সাউথ 1 ডিগ্রি 35। Now this table is, it's permanent table, it's slight variation. So everywhere of the world they use this. Suppose you want to find out the declination of the sun on, say, August 15th, আমাদের স্বাধীনতা দিবস। So then 15th August, 15th and August is তখন কত? 14 ডিগ্রি 15 মিনিট নর্থ। So therefore, this table you will need to use when you do the experiment, which I am going to suggest now. এই experiment গুলো করলে পরে একটুকু students will get some um, first-hand experience about certain basic things of position. তো এটা হচ্ছে কি নেকেড আই অ্যাস্ট্রোনমিতে কিছু সিম্পল এক্সপেরিমেন্ট আমরা যেটা সাজেস্ট করব। তারপরে আমাদের ডিসকাশনটা হবে একটা more serious discussion that, as I mentioned, that we make our observations, which is predominantly with the help of an observer and a telescope. But those coordinates which we generate there, they need to be transformed into more scientific coordinate systems which are independent of the observer. Simple experiments with the sun করব। একটা নমন হচ্ছে শঙ্কু, which is nothing but a vertical rod. তো আরেকটা জিনিস যেটা বলে দিচ্ছি, যারা if you want to do something, যে কি অ্যাঙ্গেল, এই যে আকাশে যে আমরা বললাম যে the angular separation between two objects, how you can quickly do it. So এইটা হচ্ছে গিয়ে এইটা, যেমন শুধু কোড়ে আঙুলটা যে থিকনেস, এটা হচ্ছে 1 ডিগ্রি। মানে একটা ফুল মুন ডেতে নাইটে go and if you keep your hand extended and you will find that your little finger বাঁ হাতে, সেটা যা থিকনেস সেটা অ্যাপ্রক্সিমেটলি চাঁদের যা 1 ডিগ্রি। চাঁদের কত সেটা তোমরা মেজার করতে পারো, ধর দুটো স্টারের মাঝখানে গ্যাপটা দেখতে চাও। If you keep these 3 fingers, you will 5 degrees approximately. কোর্স মোটা লোক আছে, রোগা লোক আছে, বাচ্চা আছে, বড় আছে, সবই আছে। আর এটা হচ্ছে অ্যাভারেজে আর নর্মাল হিউম্যান বিং। যদি হাত থেকে মুঠি করে রাখো, তাহলে পরে যে গ্যাপটা পাওয়া যাবে এইখান থেকে এইখান অব্দি, এটা হচ্ছে গিয়ে 10 ডিগ্রি। ধরো কোনো নেবিউলা ইত্যাদি, সেগুলোর ডাইমেনশন এরকম। আর যদি 4 ফিঙ্গার আর লিটল ফিঙ্গার মানে তর্জনী আর কনিষ্ঠা আর কি, যদি স্প্রেড করে রাখো, then the gap will be approximately 15 degrees for a normal. And if you do it this is the maximum you can generate with your hand, it will be 25 degrees. So you can calibrate these things by doing and observing the Big Dipper or সপ্তর্ষি মণ্ডল। সপ্তর্ষি মণ্ডলের একদম এইটা হচ্ছে প্রথম স্টার, এটা হচ্ছে লাস্ট। এদের এই যে ভ্যারিয়েশনটা, এটা হচ্ছে 25 ডিগ্রিজ, মানে নর্মাল একজন মানুষের ক্ষেত্রে এই যেটা বললাম সেটার সঙ্গে ম্যাচ করে। আর যদি প্রথমে শুধু এইটুকু নিই, ওই চামচের এটাকে আর কি, তাহলে পর এটা হচ্ছে গিয়ে 10 ডিগ্রির মতো। So you can calibrate that whether it is matching with this or not. So এই সপ্তর্ষির মণ্ডল দিয়ে you can calibrate your hand that whether this is matching with this kind of a general suggestion. But these are all very approximate, you can realize. আমরা যেটা করব এরপরে, যে this is the observer, এইখানে আমাদের শঙ্কুটা রাখা, the gnomon will be placed here as a vertical rod and sun will pass over this. So shadow will be cast depending on the position of the sun or the day of the year. That means day of the year যদি summer solstice day হয়, তাহলে it will be somewhere along this. ওখানে এটা হবে, that will depend on the time of the day. উইন্টার যদি ইকুইনক্টিয়াল হয়, তাহলে সান উইল গো অ্যালং দিস পাথ। তো কোথায় এটা থাকবে সেটা নির্ভর করছে দিনের কোন সময়। সো নাও দিস ইজ দি সিচুয়েশন, দিস ইজ দি আর্থ, দিস ইজ দি ইকুয়েটর, and suppose you are standing here, your latitude being pi. So your vertical zenith direction is in this, and this vertical line passing through the earth center makes an angle pi, which is nothing but your latitude. And when you actually see, this is your horizontal plane, is tangent to this circle. So this is 90 degrees. So if this is 90 degrees and this is 90 degree, and this line is parallel to our axis of plane, and this is the north celestial pole at infinity. So this angle will be equal to this angle. How it is done is very simple. You can say that this angle will be equal to this angle, or this angle, which is considered the co-latitude, be equal to this 90 degree minus. So your zenith, where you are standing, its elevation from the north direction, or north pole, sorry, north direction is this. North pole will be co-latitude. And the height or the altitude of the North Pole star will be your latitude. So actually, ধ্রুব নক্ষত্রটার যে elevation horizon থেকে, that is almost equal to your, it's one way you can measure the latitude. কিন্তু অনেক জায়গাতে হয়তো দেখা গেল যে it is not very visible, or for some other reason you want to do it in a different way, কেন এটা তো খুব accurate না, more accurate data, then there is an experiment. সেই এক্সপেরিমেন্টটা কি হয়? সেই এক্সপেরিমেন্টটা হচ্ছে গিয়ে উইল এখানে একটা খাড়া করবো, শঙ্কু অর ভার্টিক্যাল। এই যে এটা হচ্ছে আমাদের হরাইজন্টাল প্লেন, অ্যান্ড দিস ইজ দি শঙ্কু অর দি রড। সো ফোরনুন, হয়তো পূর্ব দিকে সূর্যটা, এটা যদি ইস্ট হয়, ওই দিকটা নর্থ, এটা ওয়েস্ট, তাহলে সূর্য উইল বি সামার হিয়ার, শ্যাডো উইল বি কাস্ট হিয়ার। তো দিস ইজ দি, আমরা যদি নর্দার্ন হেমিস্ফিয়ারে হই, তাহলে দিস ইজ দি নর্থ ডিরেকশন, and sun will be towards the south, and the shadow will be like this at that particular time of the day. এটা যখন ঘুরে বিকেলের দিকে চলে এলো, এখানে চলে এলো, shadow will go to this position. Shadow moves from this, প্রথমে উঠলেই শ্যাডোটা টুয়ার্ডস ওয়েস্ট হবে, and সেটিং এর কাছাকাছি সময় যদি শ্যাডো কাস্ট করে, it will be towards, but it is not only the direction of the shadow changes, its length also changes. যেমন অ্যাট মিড ডে আমাদের সেই জন্য এক্সপেরিমেন্ট হলো সবচেয়ে ছোট শ্যাডো কখন হবে, when it is at the highest point. এটা যদি দেখলাম আমরা যে সামারের কাছে, সামার সলস্টিস ডে, সামার সলস্টিস ডেতে it will rise and this will have the longest circle. This is the north direction. So midday te sun will be here and the shadow cast will be only this much. ঠিক midday te আবার winter solstice ডেতে sun will be somewhere here, 21st January, so the shadow cast will be so much in the northern hemisphere. So shadow length depend করছে on the day of the year and the time of the day. এবারে নাও আমাদের যে এক্সপেরিমেন্টটা আমরা এখানে পাবো, এটা হচ্ছে গিয়ে find out the true north, whether there is any or pole star or not, doesn't matter. We will do it with the help of sun ray. So the experiment যেটা করা হয়, that this is the north direction, this is the south direction, this is the east. So you keep on measuring the shadows, okay, and plot it throughout your day, যতক্ষণ না, and then you take a rope and you draw a circular arc. এই সার্কুলার আর্ক মানে কি, সেখানে টিপটা যেখানে ম্যাচ করবে, that means these two shadows are of equal length, and these equal length shadows, if you bifurcate this angle or bisect this angle, this will give towards the true northerly direction. Exactly. So this experiment you can do very easily with a piece of top, rope, and a vertical pole, and on a sunny day. So এখানে যেটা করতে হবে, you have to record the length of this at maybe 10-15 minutes interval, or even not half an hour, 15 minutes will be good. And you have to draw a circular arc and to see that which shadows are of equal length. তো ওই দুটো শ্যাডোকে নিয়ে তাদের টিপ দুটো যেখানে আছে সেটাকে নিয়ে join this, this will go, this is called the shadow line, and this will point towards east, and if you bisect this, it will point towards, this is the true north and this is the true east, and of course the south and west can be easily done. It's a খুবই simple experiment, and I think Subroto should be able to help the students to create the situation when they can find out. And each one you can do separate experiment and find out the direction, and you can do it with the help of your some kind of cardinal direction of the building you are in. Suppose UEM building, you can tell that buildings a particular important wall. What is the angle it makes with the true north direction? Something you can always find. So this is so therefore this is discussed on a flat horizontal plane with the gnomon base as the center. Then the tip of the shadows at suitable intervals can be marked. These tips are then joined by a smooth curve, and wherever the curve cuts the circle which you have drawn, be marked as A and B. তার মানে এই দুটো পয়েন্টে shadows are of equal length. And then the perpendicular bisector of this line AB, that points to the true north. Once the north is determined, south, east, and the west can be determined. Best result can be achieved by using shadows at suitable times. All the shadows have not been shown to the figure neat. The north direction has been shown by the red line, and it is to understand that the shadow line shown in black points towards east. আরেকটা জিনিস হচ্ছে গিয়ে এটা আমার সলস্টিসের কাছাকাছি করলে একটু অসুবিধা হবে বিকজ অফ আওয়ার latitude. Our latitude is very near to Cancer. That means the sun will be almost overhead and the length of the shadow will be small. So do it sometime, like say, for example, some equinoctial time or some September or so that you will get enough length of the shadow. So this is the experiment I will suggest you do to get a first-hand experience in detecting or finding or deciding your exact true north without using any compass or anything. Now, determination of the latitude. The latitude of the place, suppose you want to find out the EM building's latitude. The latitude of the location can be also found out by measuring the length of the mid-moon shadow along the north-south line. এখানে কিন্তু you have to find out the length of the shadow at the mid-moon, that means when it is the smallest. Before proceeding further, study the figure I am showing. It shows the celestial sphere with the important lines and the sun on the ecliptic at a place. The coordinates used in astronomy are right ascension, which is equivalent to longitude, as I mentioned, in terrestrial case, and declination, that is equivalent to latitude. And so on any day, the position of the sun on the ecliptic can be defined by two parameters. Now you can see this diagram. I'll explain this, and this is important diagram. Say, you are here. This is your local horizontal plane, and this is your vertical zenith. And you have a shonku or a gnomon, which is vertical. That you have to check. Take the vertical by the what is আমাদের রাজমিস্ত্রিরা যেটা করে ওলন বলে যেটা বলে by hanging something so that it goes directly vertically downward direction. So that is easy way of finding the actual vertical direction. And this is the local north direction is data north point. Celestial pole টা এদিকে আছে। Now it is the axis of rotation of the earth. Now this is the equator. If this is the axis, so the equator will be like this. And if this is your location, the latitude is this angle, phi. Now, another thing that sunটা কোথায় থাকবে? Sun will be always on the ecliptic. So this is the ecliptic line. So ecliptic circular sunটা এখানে আছে. So suner যে elevation যেটা declination সেটা হচ্ছে গিয়ে declination of the sun on that particular time when you are conducting the experiment. And this is the instant when it is at the highest position, midday. John shadow will be the shortest. So sun is at a long distance, so all the sun rays will be parallel to this So sun ray will be like this, and the shadow cast will be this length. And Norman height is this much. So therefore, note these quantities. This angle is the declination of the sun on that particular day. This is the midday position when the shadow is the shortest. Shadow length you can measure. Height of the gnomon is known. The latitude is this angle. And co-latitude হচ্ছে গিয়ে এই অ্যাঙ্গেলটা। এগুলো সব শিফট করে গেছে, আই ডোন্ট নো হোয়াই ইট হ্যাজ শিফট। সো এই এক্সপেরিমেন্টার যে একটা লোকেশন উইথ ল্যাটিটিউড ফাই অ্যান্ড জেনিথ ইজ ভার্টিক্যালি আপ, এটা আমি সব দেখালাম। সো নাও এখন কি করে আমরা বার করবো ল্যাটিটিউডটা? ল্যাটিটিউডটা লেট মি শো ইউ উইথ দি হেল্প অফ দ্য ডায়াগ্রাম। এটা হচ্ছে গিয়ে অ্যাক্সিস আর্থের, is the group, and is the equator, and sun is somewhere here, and sun declination angle together, and the observer is located here. So this is the vertical শঙ্কু যেটা আর কি, height h, and the shadow cast will be, the sun rays will be parallel to this, and the shadow cast is this much. See shadow length L যদি বললাম. So this angle can be found out. And this angle is phi, latitude. So how to find out this angle from this data? You can see that your declination is known. So therefore, the angular magnitude will be what? This angle, if you can measure, how much is that? Tan of that angle. Say this angle is psi, h by a. Now how it is located with latitude? Latitude will be what? This angle. And this angle what you have got measured, or if you draw parallel line, this is one line parallel line, this is one parallel line. So this angle will be equal to this angle. Rather, let us call this as. So this is alternate angle. These are two parallel lines connected by a straight line. So these angles are equal, we know from our school geometry. How much is this psi? Tan psi is equal to L by h. You can easily measure the shortest height or shortest length of the shadow. Height of the trunk is known. So you can measure this angle. It will be tan inverse L by h is equal to psi. How that is related to our latitude? Now phi is given by this angle psi plus declination. So declination is given from the table. You can consult the table, and on the day when you are doing this experiment, you find out what is the declination of the sun. And that angle you add with the angle which you find out by the measuring the shadow length and the gnomon. So this will be your latitude. And this way you can find out and do the experiment carefully. You can repeat the experiment a few times because it is any experiment will have some errors, and then find out that what actually the value you are getting. And compare this phi is equal to tan inverse shadow length by gnomon height plus delta, which I have showed you just now. This is the declination of the sun on that particular day. Now, this experimental value which you get of the latitude, you can compare with the one available from the internet. You can find out what is the latitude of Calcutta and see how accurately you have been able to do the exam. So I thought that, if there is any question, we can discuss it. এই ফিগারটা যেটা হয়েছে কি, এগুলো শিফট করে গেছে। এইটা হচ্ছে সাই, which is equal to this angle. So you have to find out latitude, which you have to add psi and the declination angle. When declination is positive, it will get added. When declination is negative, automatically it's deducted. Because then the shadows will be longer and you have to deduct this. That you can easily see this diagram. But main thing is to understand that this sun ray and this direction, these two lines are parallel because sun is at an infinitely long charge distance. And you are connecting these two parallel lines by a straight line. Therefore, these alternate angles are equal according to our school class 8 geometry. And so you know this angle. And only thing you have to add the declination to get your length. Is it okay? So when do you propose to, you will get a reasonably good shadow length, you have to do the experiment to find out the length of the smallest shadow. That will be the important thing you have to keep. So generally what they do, they plot this curve like this. Shadow length এরকম হয় like this, this. So this join the tips and then find out the shortest distance. Actually, if you already have determined the north direction by this kind of an experiment, the shadow which is along that direction will be automatically the shortest. So you need not plot everything, but if you have marked your north direction, measure the shadow along that, when it is along that.